So thank you very much for inviting me to give this talk. I'm happy to meet you all virtually and discuss a little bit about my research. And next time I hope to come and meet you all in person. But this is the Zoom life now that we're all accustomed to. All right, so as the title of my topic describes, and the abstract, what I want to discuss today is something known as quantum resource theories. And this is a subject that I've been interested in for about the last 5 or 6 years. And it's kind of a general area that covers a lot of different subtopics within quantum information. And what I hope to do here in this talk is just give you a brief sense of what it means to talk about a quantum resource theory and why it might be of interest to you and how it somehow simplifies and sheds new light on some concepts that maybe we've heard about, but we haven't really thought about precisely. So throughout this talk, please don't hesitate to ask questions. I'm not quite sure all of where your backgrounds are as far as quantum mechanics or quantum information, but just stop or put it in the chat, and I'm happy to be interrupted mid-sentence even. So no worries. Okay, so the outline of this talk will go as follows. What I'd like to do is start kind of just by generally motivating this resource theory philosophy is what I like to think of it as. But I want to start with some observations within thermodynamics and also statistical decision problems. And then we'll define the structure of a quantum resource theory and some general properties that you encounter when you start dealing with resource theories. We'll talk about states versus channels, which is the static versus dynamic resource theories. I'll describe a quantum resource theory of measurement compatibility. So this is when we're dealing with incompatible observables. How can we think about that as being a resource theory? And then also some current and future work. And here I'm going to talk about quantum non-locality. So how can we think of non-locality as being some sort of resource that we use in quantum information processing? Okay. So let's begin with putting on our thermodynamics cap. And I want to consider just a very simple system, which consists of a cylinder with a piston. And let's suppose that this piston is sealed such that the cylinder inside contains a fixed number of molecules, and they're all the same species. So we simplify this as much as possible. And there are kind of two parameters in this setup here, V and U. So V is its volume, and U is the energy. All right. And then each value of V and each value of U is a pair that we can identify as the state of our thermodynamic system. And well, what we can do is we can, of course, compress or enlarge this volume here. We have a piston there, so we can raise and lower it. And what will that do? Well, we'll go from one V1 to V2, but our energy will also change. We'll go from energy U1 to U2. So this can abstractly be described as a state transformation. We've gone from V1 U1 to V2 U2. All right, good. So we can draw this now on a plane here, a UV space here, where the initial point is our state 1, and we've done a transition into state 2. All right, and in principle, you can realize any state transformation on this grid here if you're allowed to add or extract arbitrary amounts of heat or work. So what I mean by this is if you give me a pair, say V prime and U prime, and I start from some other pair, I can always reach that state provided I put in enough heat, do enough work, or extract enough heat or work, right? So we can always realize any state transformation. So on the surface, like this idea is not very helpful because we can basically do anything. But it gets interesting when we start placing restrictions on the allowed processes. All right, and once we start putting restrictions on what's allowed, then there will be limitations on what state transformations we can achieve. So one of the most standard restriction to consider is the class of adiabatic processes. All right, now you might have heard of this, and if you take an intro thermal class, you certainly have seen this before. But let me kind of describe it to you qualitatively how this works. So in an adiabatic process, what are you allowed to do, or what characterizes an adiabatic process? So we start off with our piston in some initial state, and then you can introduce some other device And this device can be quite general, such as a motor or a heating plate or something else. But we note the initial state of that device, call it gamma 0. Then we hook up a weight to this device, all right? And it's in some gravitational field here. And what we do then is we interact the device with our system. And this interaction then is going to draw work by lowering this weight, right? So it's basically going to convert the gravitational potential energy into mechanical work, which is then going to change the state of our system. All right, and then the one thing that we require to isolate just the change of our system and the change of the weight is we demand that our device has been returned to its initial position or its initial state. All right, so whatever we do through this process, this characterizes an adiabatic process, right? And the key part here is that any change to the system is accounted for by the mechanical energy of the weight rising or falling, right? Because our device has basically stayed the same, right? It started off in state gamma 0 and it ended in state gamma 0. So everything, all changes can be deduced to the change mechanical energy of the weight. All right, so now we can ask if these are the rules of the game, if we're only allowed to do these sort of transformations, what state transformations can we realize? And let's use some symbols here. So if I have a state X and a state Y, let's say that, let's use this pre-order here. So X is majorized by Y. We'll say this denotes if it's possible to go from X to Y by a process that I just described on the previous slide. Okay, and the fundamental result, which is known as the second law of thermodynamics, is that you can go from X to Y if and only if the entropy of Y, this is S is the entropy of the state, is no less than the entropy of X, of the initial state. So the final state has to have no smaller entropy than the initial state. And if that holds, then you can find some sort of process, adiabatic process, that converts X to Y. Okay, just as a side note here, this relationship, this X majorized by Y, this forms what's known as a total order. And all that means is that for any two states, X or Y, you either have X is majorized by Y or Y is majorized by X, or they're both, or they both majorize each other. So that characterizes what's known as a total order. And I make this remark here because we'll see in this talk that we don't always recover a total order. Okay, good. So this is the first example, and this is actually a resource theory here. We'll see why, but I just want you to be aware of thinking in terms of this restricted operations and this idea of a second law of thermodynamics. I'm going to turn to another problem now, and this is what's known as a statistical decision problem. So there's no physics whatsoever in this problem, well, at least explicitly. This is more of a game. And the game is goes something like this. So you imagine you have some source, or in this case, you can think of it like a die. So this is a category die. If you've ever played categories, you know you have this die that has, I don't think it has all the letters of the alphabet, but it has quite a few of them. And then you roll it, and then whatever letter shows up, that's the letter you use to match to choose things from certain categories that begin with that letter. So we can think of this as like a random number or random letter source here, and then X is the letter that is produced. All right. Now here we are over here. This is us with our magnifying glass. But unfortunately, we don't get to see X right away because there's some noisy channel that introduces some noise to X. So maybe with a very small probability, it causes X to switch, or there's some noise that's introduced in this channel. And actually what we observe is Y. All right, so there's been a transition from X to Y. All right, now we see Y and we need to make a decision about what the value of X was based on Y. So we apply some decision function, D, and then our guess is Z here. All right, and so then we can identify what's known as a payoff function. And this is a function of both X, the original value of the letter, and then also our guess Z. And the value of this I'm going to denote by a $sign. Okay, so this payoff function could be arbitrary, but it's some way of quantifying the relationship between our guess Z and the initial input X. So if we imagine that this die is uniform, then the average payoff would look something like this, right? So here we're basically sampling 1 over the size of our die. And then, so X comes out of the die, then it goes through this channel, and then we apply our decision function. And then this is the value, the $sign we get out. That's our payoff. And so now we sum over all Y's here that come out of the channel, and that's our average payoff. So in this game, the experimenter is going to want to choose a decision function D that's going to maximize this payoff. So we suppose that the payoff is fixed initially, and then the goal of this problem is to come up with a decision function that gives you the largest average payoff. Okay, and so then we can define this value. Let's say the max payoff. So what we do is it's this average value, but then we maximize over all decision functions D. All right, and this is actually some measure of our channel, because notice that it's for any channel n and any payoff function omega. I can define this quantity here. So it's somehow quantifying a property of our channel for a given payoff function. Okay. Right. As I just said, for each payoff function, this payoff, this value here is a figure of merit for our channel. So now let's kind of bring it back to this idea of transformations. So suppose we want to transform our channel. So we started off with n, and we now transform it to a new channel m. And here's your first clue of that this is connecting to what we did previously. This is analogous to a thermodynamic state transformation. Okay, we've started off with some initial object and we're converting it to another object, just like we did with our piston. And the question we ask is, how does this max payoff function compare? When we transform from n to m, how does our max payoff change? And well, okay, it's going to depend on the type of channel transformation we perform, right? Just like in the thermodynamics case, how this value changed depends on what operations we did. So we considered the class of adiabatic processes. And here, what I want to consider for our channel transformation is what's known as post-processing. So in pictures, it looks something like this. So here was our channel, our initial channel. And then what we'll do is whatever comes out of the channel, we're going to run it through another channel K. Okay, so we had an X to Y, and now we cause another transition Y to Y prime. And what does this do? Well, effectively, if we zoom out, we get something that goes from X to X prime. So this is some new channel. So we went from an N, original channel, to a new channel M, just by tacking on a post-processing object here. Okay, and so now let's introduce this majorization notation, and we'll say for any two channels N and M, we'll say that N is majorized by M if we can convert the first to the second by this post-processing. All right, and intuitively you can think about this as when you introduce this K channel here, this post-processing, it's like somehow adding more noise, right? I mean, this initial channel N was noisy, and now you're adding a second channel to it, so now you've added even more noise. So we can say that N is somehow more informative than M, right? Because M, you have like another layer of noise. So you've lost some information with this channel M compared to N. So in our decision problem game, it would look something like this. So we had our noisy channel, and then we put in our post-processing. And now you have to make a decision based on that post-processing value Y prime. Okay. Right. So now there's this famous result by three different people independently. Well, this is now 60-some or 70 years ago, actually, this BSS theorem, which relates this idea of channel convertibility and payoff. And so what it says is that you can convert N to M by this post-processing if and only if the max payout for N is no less than the max payout for M for all possible payoff functions we can define. Okay, and right, so this is basically telling us it's kind of relating two things. On the left-hand side, this direction here, this is a physical process. You're starting with one channel and you're adding another channel. And on the right-hand side, this is kind of a mathematical relationship, right? It's telling you about an average payoff that you get playing some game, some decision game. And so the nice thing about this BSS theorem is that it shows that you have a physical correspondence between transforming your channel, and it relates it to this mathematical payoff for a game that you're playing. Okay, and again, this comment is that now we're dealing with a partial order, because in fact, instead of just having one relationship, this has to hold for all payoff functions omega. All right, let's now enter the realm of quantum. Let me pause and actually see if there are any questions.
I had a quick one.
Yeah.
I was curious about how the payoff functions are being defined, because in the most absurd case, which is obviously not useful, you could define a payoff function that has value 1 if you return, for example, if we're doing the letters of the alphabet, you could define that your payoff is 1 if your letter is Z and it's 0 otherwise. And if you have a post-processing channel that takes everything to Z, then obviously M would be better than N in that instance, although it's obviously not useful.
Right. So I guess, yeah. So in the theorem, you actually you allow for any possible payoff functions, even ones that you would never even want to consider. You can, so the theorem itself holds for any payoff function, but in practice you wouldn't really want to consider those, like the ones you just decided or you just described, right? It wouldn't correspond to anything advantageous to the house or the player, whichever side is you're considering. But the point is that you could, I mean, the payoff function itself is just a mathematical function. And I guess the point I was trying to make is that you have this mathematical relationship on the right-hand side where omega could be anything, and you've related it now to this convertibility, this physical process. Mm-hmm. So you're right. I mean, probably what you would normally play is you would win if Z is equal to X, right? Like that's the most obvious one.
Yeah, I was just curious because that is a valid post-processing. And so in that case, I guess in that case, the M that I've defined would not majorize any N. But it is still a valid choice.
Correct. Yes.
Okay, yeah.
Okay.
I've got a question, too, and this is on the channel.
Yeah.
Maybe see the channel slide. So you described the box with the M channel, N and K, in words, sort of saying, this is going to, if anything, add noise.
Yeah.
So what if your channel N is, let's just sort of view it as a well-behaved unitary. Okay. And presumably for any X, it gives sort of 1-to-1 mapping on Y.
Okay.
Then what if K is the inverse of that unitary, which it just exploits the fact that there's a 1-to-1 mapping of X to Y. And so now you're going to use that same mapping in the other order to go from Y to Y prime. Is that allowed in the scenario you're talking about? That one presumably doesn't change the information or add noise at all.
Right. Okay. Yeah, that's a good example. Actually, so in this case, we're dealing just with classical values here. We're not quantum. So it wouldn't be a unitary, but the analog there would be a permutation. Okay. So basically you could imagine N just permuting your inputs and then K undoing that permutation. And so then I guess, maybe I shouldn't say is more informative. In that case, I would say that N and M are equally informative. So I guess the statement would be that M is no more informative than N. I think I need to change the way I worded this.
Okay.
Because if you can, if I do a permutation to letters, then I haven't really changed the information content of that. I mean, I can always just, like you said, I can always undo it. So there's really no loss of information in a permutation.
Right, okay.
Yeah. Yeah, thanks for that. So that needs to be rephrased. That's a good example that you gave.
Okay, good, thank you.
Okay. All right, so now let's look at a third example. And so now we're entering the realm of quantum mechanics. And so let's consider two quantum systems that are controlled by Alice and Bob. For instance, this could be a pair of photons. And let's say their joint state is given by this vector here. And for those who maybe are not too familiar with notation, this is just what this is known as a ket here. And this is just describing the joint state of these two photons, right? So we have two photons, and we prepare them in some way. And whatever that state is, we're going to write by psi here, psi AB. All right, and in general, this can be some entangled state. So what I mean by entangled is that you might not be able to factorize this state into an individual state for A and an individual state for system B. They might be entangled, so you can't introduce a tensor product here. Okay. So now suppose that Alice and Bob want to convert their systems into some other state phi. Right? So you start off with one entangled state, and you want to go to another one. And again, in principle, any state transformation is possible if you're allowed any type of physical interaction between both systems. Right? In fact, you could just construct a joint unitary that rotates psi into phi. So that's possible. But what we're interested here is when certain limitations are placed on the allowed operations. Okay, so what are these limitations that we're interested in? Specifically, we're interested in spatially separating Alice and Bob. So we're going to consider them to be in separate laboratories. And what they're allowed to do is they can perturb their system, they can measure their system, they can interact their system locally. So they each have control of a subsystem, and they can manipulate their subsystem locally. And they're allowed to exchange classical information between the two laboratories. So this AM here, this just indicates that Alice is doing something on her subsystem, and she's sending message M1 to Bob. Well, then Bob hears M1, and then based on this classical data that he learns, he does something in his laboratory, which we can describe by this BM2. And M2 is maybe he makes like a weak measurement on his system, and he gains some classical information M2. He sends this back to Alice. And now Alice does something based on both the M1 data that she sent to Bob and the M2 data that she received back. She does something, and this kind of goes back and forth. It's kind of like a ping pong bouncing back and forth between the two laboratories. And these are the free operations that I want to think about here. And the key point here is that only classical information is exchanged between Alice and Bob. Okay. So physical processes of this type are known as local quantum operations and classical communication, or LOCC. All right, this is a really important class of operations that's studied in quantum communication because, again, it's just involving local quantum processes with exchanging classical information between the laboratories. All right, so let's go back to our question. We wanted to know when you could convert psi to phi. And so let's introduce this majorization notation again. And we'll say that if you can go from psi to phi by this ping pong process, this LOCC, then we'll say psi is majorized by phi. All right, and so this problem was solved by Michael Nielsen in the late 90s, where he gave conditions for when you can do this transformation. And it turns out that if you analyze these state vectors sine phi, if they satisfy a particular relationship, which is related to something known as the chi-fan norms, but that doesn't really matter here. The point is that there's a set of finite inequalities that need to be satisfied between the two state vectors. And if you satisfy those mathematical inequalities, then you're guaranteed that you can convert psi to phi by LOCC. So again, it's this nice correspondence between here on the right-hand side, we have mathematical relationships between our vectors. And on the left-hand side, we have some physical process of converting one state to the other by this distributed LOCC process. Okay, so here's the summary so far of what we've seen. You can see there's a common structure. So in both cases, we're talking about state transformations. And sorry, in all three of these cases, there's state transformations. And we've characterized when it's possible to do these transformations in terms of some functions. So in the adiabatic case, it was that the entropy of y needed to be larger than the entropy of x. For this channel post-processing, you had to have this payoff, max payoff function had to hold, had to be m had to be no greater than n for all payoff functions. And for this LOCC convertibility, we've introduced these measures here that have to satisfy this inequality. Okay, so lesson one of the talk is that placing constraints on physical processes lead to partial orderings of objects. And objects here, in this case, we're talking about states of our systems. And then the second lesson is that these constraints then lead to certain quantities that cannot be increased, right? That's another way of looking at this. So if I'm going, for instance, if I'm going from X to Y by an adiabatic process, we know that the entropy cannot decrease. If I go from N to M by channel processing, I know that my max payoff can't increase. And likewise, if I go from psi to phi, I know that these E values can't increase. And so we would actually interpret these E values as being some measure of entanglement. And so what we'd say is that going from psi to phi, you're not, by this LOCC, you're not able to increase your entanglement. Okay. And so what we'll see now in our the broader framework we're developing here is that these are resource quantifiers, these quantities here that are dictating the transformations. All right. So now I want to kind of generalize this whole discussion under the framework of a quantum resource theory. And to do that, let me just give a quick primer on this meaning of quantum operations. I think I've used this phrase already. And if you're not familiar with it, this slide will hopefully give you an intuitive picture of what this means. And in practice, what it's referring to is the most general type of evolution that of a quantum system that an experimenter can perform, at least ideally speaking. And it looks something like this. So you have your quantum system S, and okay, yes, sorry. So what are we allowed to do? Well, actually everything quantum mechanics allows. So what does this look like? So you have your quantum system S, and you introduce another ancilla system R here. Okay, so you have your primary system, and you have now you've introduced a secondary system R, and then you introduce some interaction Hamiltonian between these two for a certain amount of time. And what this will cause will be some unitary dynamics, assuming our system here is nice and closed. Now you have this unitary dynamics on your two systems. And then at the end of the day, what you do is you measure your ancilla system, okay, and you learn some classical information by measuring this second system. And your quantum system will then have undergone some transformation through this whole thing, S prime. So abstractly, if we kind of just think of this as like a black box, let's see what's happened in this black box. So we input some quantum system S, and what we got out was a quantum system, but we also got some classical data out as well. All right. And when we speak of quantum operations, we're thinking of things like this. It's you have some quantum in, and then you have some quantum out, but also some possible classical out as well. And mathematically, this is described by what's known as a completely positive trace preserving map. Don't need, maybe I bring this up now because you might have heard this in the literature, what this is. If you haven't heard about it, don't worry about it. It's mathematically describing this process of going from a initial set of density matrices to a final set of density matrices. And this is also what's known as a quantum channel. Okay, so I'm going to use this word quantum operations, and I'm referring to things like this, these type of quantum channels. All right, so let's define now what a quantum resource theory is. So there's two key features to a quantum resource theory. One is that for any two systems, S and S bar, we identify free sets of density matrices. So these are like free states that we're allowed, Fs and Fs bar. And we're also defining a set of free quantum operations. So O is some set of operations that are transforming S to S bar. And the constraint that must happen for O is that if I start off with some object, rho that's free in my initial space, my map must send me to a free state in the target space. So it might be easier to see this graphically, but what any operation in this set O here, it's going to always map a free state to a free state. Right? So I start off here, it's always mapping a free state to a free state. If E belongs to the set O, then it has to have this property. It needs to preserve the freeness of our states, is one way of thinking about it. It can take a non-free state to a free state, right? That's possible, right? But you can't go from a free state to outside the free state. So it acts invariantly on this set of free states. And anything outside the free states we're identify as a resource state. Okay, so we're kind of doing this like coarse graining of the set of all density matrices. We say some of these density matrices are free and some of them are resources. And then on top of that, we're also defining these maps or these operations, which have the property that we can't generate resource from free states. Okay, so that's kind of the basic structure. And we've already seen this in play with our three examples. Let's go back and look at entanglement, because this is actually the prototypical quantum resource theory. So here our free operations are LOCC, right? That's this set O here that I defined. This is what you can do for free. And the free states are those that can be generated by LOCC, right? Our free maps always take a free state to a free state. So what can we generate by LOCC? Well, if we go back to this ping pong diagram here, if we start off with say a product state between the two laboratories, and we do this LOCC, we'll end up something that looks like this. We maintain the product state form, and if this product state form here, this type of state is what's known as a separable state. Okay, so if you ever see this in the literature, or if you're reading and you see states that have this probabilistic combination of product states, this PM forms a probability distribution. If you see this is what's known as a separable state. And the link here is that states of this form, this is what you can generate by LOCC. Any state that has this form you can generate by doing a ping pong protocol like this. All right. Conversely then, if it doesn't have this form, if it in fact does not have the separable form, then you cannot generate it by LOCC. And this leads us to now an operational definition of entanglement. So if I ask you, what is entanglement? What does it mean to say something's entangled? You might kind of pause for a moment, think about it, look in the textbook, look in Wikipedia, and there'll be some mathematical definition. But here I want to give an operational definition to entanglement. And so the operational definition is that a quantum state is entangled if and only if it cannot be generated using LOCC. Okay, so I say operations because it's defining what's the more primitive object here is the operations. It's the LOCC, it's the restricted operations. That's first what is like the more primitive object, and then we define entanglements as those things that cannot be generated by our free operations. Okay, right. So the two objects in a resource theory are your free operations and your free states. In entanglement, we have a great example here of LOCC being the free operations, and the free states are the separable states. All right. So why study quantum resource theories? So I'll give you some reasons here. There's some practical reasons. So first, the free operations, you can choose these to reflect some realistic experimental constraints. So in the case of LOCC, it's somewhat reasonable to think that it's easier to locally process your quantum information than to send it over long distances on some fiber optic cable, let's say. So that may be very challenging to do, to send quantum states from one lab to the other. On the other hand, if we can isolate our laboratories, we have better control locally than we do by sending quantum states long distances. So that's one example of an experimental constraint that kind of lends itself to this mathematical analysis. Another reason is it allows us to quantify the resourcefulness of different quantum states and processes. And we'll come back to this in the next slide. You'll see this. And it also helps us identify methods for transforming resources from one to the other. So if you create something in the laboratory and you want to know, hey, I've got this one great setup and it's allowing me to create states of this form. What can I do with these? Are there other states I can generate using my same setup? What can I do with it? And so that's kind of the resource theory perspective. It's like, all right, let's identify the things we can do with the free operations. And let's now take what you've been able to generate and convert it into something else. Maybe that provides greater utility for another task. So those are some practical motivations. Fundamentally, what I'd say is that this does provide a way to operationally define primitive features of quantum mechanics. So on the previous slide, I defined entanglement in terms of this LOCC. You can do the same thing with non-locality, and you can do the same thing with measurement compatibility, or incompatibility, and hopefully we'll get to that example a bit later. All right, and then a final element of this is it allows us to unify different aspects of quantum and classical information under a common theoretical framework. And we've already seen this in play here, right? When we talked about the similarities between thermodynamics and statistical decisions and entanglement. So we saw three different tasks that seem on the surface to be quite unrelated actually have this nice common framework. All right, here's a kind of a non-exhaustive list of resource theories that have been studied in the literature. We've looked at entanglement here, and so quite a bit of work has been done in this area. One area that might be of interest to folks here who are interested in quantum computing. So you can actually do a resource theory of quantum computing, and here the free operations are typically identified as being Clifford operations. And then the question is, what can you do with these Clifford operations? Or maybe you can add some other processes beyond Clifford. And so then you have some limited gate set or some limited set of operations, and you want to know what you can do with those. And that's one approach to a way to tackle quantum computing from like a resource theory perspective. And then there's also, you can study quantum foundations from this as well. So for instance, non-locality, contextuality, and there's also a resource theory of knowledge that has been proposed. Let me talk a little bit about some general features. So I mentioned that this gives a way to quantify how resourceful an object is. And so you can ask the question, how much resource is contained in a given state? How much entanglement does the state have? How much coherence does the state have? How much non-locality does the state have, right? These are questions you could ask. And so we want to actually come up with a very precise way of addressing these questions. And so first of all, there's not one single way to measure resource. Usually it's with respect to some particular task you have in mind. But a golden rule that all resource measures should satisfy is that it should be non-increasing under the free operations. So what I mean here is that if you say phi is going to be some measure of resource and E is a free operation, then I can't increase the resource under E, right? So I have to have this monotonically decreasing process. And in fact, this is just what we saw in the thermodynamics, for instance. You can imagine phi here is entropy, or rather minus phi would be entropy. And then E here would be some adiabatic process. And then this is exactly a second law of thermodynamics right here. So that's why it's kind of known as a golden rule. Right, okay. There's just some examples. All right, one general way of defining a measure is what's known as a distance-based approach. So here you have in your set of density matrices, you've isolated your free states, and now suppose you have some state rho outside of it. What you could do is you could ask, well, how far is it to the set of free states? Right, so I'm letting D be some distance measure on the set of density matrices, or rather on the space of Hermitian operators. And then I try to minimize the distance, mathematical distance from the set free to my density matrix rho. And this provides a good way to a good resource measure. So there's what's known as a trace distance of resource. There's a relative entropy of resource. If you use the relative entropy measure, it's not a true measure, but it works very well actually for quantifying resource. And kind of one nice practical application here is that if this set of free states is convex, then mathematically you can identify what's known as a separating hyperplane. And in the literature, this is sometimes known as a witness. And all that this object is, it has the following feature. So for any rho that's not in my free state, I can find one of these witnesses and it satisfies this property that the expectation, so W here is a Hermitian operator, so it's an observable. And what this witness says is that if my omega belongs to the free states, then my expectation of OW will be non-negative. On the other hand, for rho, my expectation will be negative. So it provides a way of, this is known as witnessing your resource. Basically, if you prepare in the laboratory some state rho and you want to know whether or not it has entanglement or whether or not it has some resource, you can use this method. You identify a witness, which is this observable, and you evaluate its expectation. And if it's positive or if it's non-negative, okay, you can't say much. But if it's negative, then you know for a fact that, in fact, this density matrix has resource. This is a nice experimentally friendly way of actually identifying resource. Okay, good. Let me pause right now because we'll enter the kind of the last part of the talk. But are there questions up to now? All right. Good. So I want to now go one step more general and introduce a distinction between static and dynamic resources. So the things that we've been discussing right now have been states, as far as the quantum states that we've been talking about. And so you can think about this as being a static object, meaning that it's kind of like something that's fixed in time. You prepare a state, and assuming that it's not interacting with anything, it's just there. It's a snapshot, and you keep it fixed in time. On the other hand, you could have a dynamic object, which inherently is transforming some input to an output. So this is what we would say is a dynamic object, which would be a channel, and a static object would be a state. And so what we want to do is we want to extend the resource theory formalism to the study of channels as well. And this is quite natural to do. In fact, all of Shannon information theory can be seen as a dynamic resource theory of communication. And here in Shannon information theory, you can think of the noiseless channels as having maximal resource, right? And the free channels would be those that have zero capacity. So you could formulate all of actually classical information theory from this perspective as well. So it's kind of a nice general framework. But now let's go on, and in the static case, we had free states and we had free operations, which were channels acting on our states. Now when we go to dynamic objects, the free states, I say states in quotes, but these are now channels, right? And now the free operations, what are these free operations? Is they're transforming one channel to another. Okay, these are sometimes called supermaps, or they're also referred to as quantum cones. So how do we convert one channel to another? We've already seen an example of this when we did the statistical decision problem. We had this post-processing that converted one channel to another. You can do more general things. So here on a quantum channel, what can we do? So we could introduce a pre-processing map, right? So we started off with this channel here. We introduce a pre-processing operation, and we could have a post-processing operation. And then what we can do is we can connect the two with some side memory. All right, and if we then zoom out, what have we done? We now have a new channel that's transforming T to T bar. So we started off with something that went from S to S bar, and using these objects, pre, post, and then a side channel, we have a new channel going from T to T bar. Okay, so this is kind of how we approach a resource theory of channels. A dynamic resource theory is now we're thinking in terms of these pre, post, and correlated side memory. That's transforming one channel to another. So I want to do this now to a particular type of channel, which is known as a measurement device. So let's think about what a measurement device does. At a high level, you can think of a measurement device as a QC to C channel, right? So you have a quantum state that goes into your device, and you also have some instructions, some classical instructions that you've fed your machine. And then what comes out is your measurement outcome. So you have quantum input, classical input, and then a classical output. All right, so let's ask, what sort of resources could be present in such a device like this? And well, one thing is that quantum memory might be a resource. So this device may need to store the classical instructions until, this device may need to store the quantum state until the classical instructions arrive. Right, so you could imagine that if you want to get this thing working precisely in time, you might need some quantum memory here to hold the quantum state in until you have classical instructions arriving. And you could think about this, maybe this is one little subroutine in some larger circuit, right? So you could imagine this connected up to another node, and you have this interaction between the nodes. And in fact, there's some delay time for the classical instructions to come from one node to this node, but your quantum state has already arrived. So you would need to have some quantum memory here in general in order to wait until you receive those instructions, and then you can do the next step in your protocol. Okay, and what I want to argue now in the next few slides is that this quantum memory demand is operationally, it's equivalent to the resource of measurement incompatibility. All right, so ultimately, this result here that I'm going to try to sketch for you guys is a linkage between quantum memory and measurement incompatibility. So let's talk about incompatibility for a moment. Historically, this has been understood in terms of what's known as joints measurability under sequential measurement. So if you've taken a quantum mechanics course, this is something you see usually in the first few months of the class, is this idea of the order of observables mattering, right? This is a quantum mechanical feature. So if I have rho and I have some observable A, right, and I first do A, I measure it, so I get my outcome here, and then I have another observable B, and I get outcome B. This will define some probability distribution over the outcomes, P1, right? So A, B. But now I do the experiment where I switch the order. First, I measure observable B, then I measure observable A. All right. And so this will give me some other distribution, P2, over my outputs. And what we know is that in general, these P1 and P2 are not going to be the same. Right? So the order of measurement matters generally in quantum mechanics. And so if they're not equal, then we say that A and B are incompatible. Okay. And really what this means is you can't define a joint probability distribution over the outcomes of these observables, right? Because it depends on the order of measuring. So a classic example here is a Stern-Grirlock experiment. So suppose you prepare your spin state in the up direction and in the z direction. First I measure, my first observable is to measure in the z direction. And then my second observable will be to measure in the x direction. And so I can ask, what's the probability that I get both spin up in both the z and the x direction? Okay, and you can compute this, it's 1/2. But now let's switch the order of observing. Okay, now first I measure the x direction and then I measure the z direction. And then I can ask, what's the probability that I get both spin up? And it's 1/4. Okay, so x and z here are not compatible observables. Oops. Okay, and again, it's in the sense that you can't define the joint distribution over the probability of the spins. Now, for observables, it's fairly nice because we have this condition that they're incompatible if and only if they don't commute, right? And you can understand this in another way. So if they do commute, then we know that they're simultaneously diagonalizable, right? There's a common eigenbasis for both the observables. So we can take their spectral decomposition. And then what you can do is so here's the common eigenbasis, EK. So the way that you can measure both A and B simultaneously is you project onto this eigenbasis, and then you do some post-processing, which is usually just some coarse graining. So we can realize this by first measuring in the eigenbasis and then doing coarse classical post-processing. So a circuit here looks something like this. I feed in my state rho, and then I project out into the common eigenbasis of the two observables, right? And K is my measurement outcome. And then I can feed this to two different channels. My PA channel, this is going to realize observable A. So this outputs A here. And my PB channel realizes observable B. So notice here that this is classical information, right? So we've actually kind of cloned it, right? We've split it. We made a copy here. We fed one to this channel, PA, and we've fed another K to this channel here. And that gives us then a joint distribution, PAB. And so this is well defined because we can do this process. We have a common eigenbasis to the two observables. All right. Another way of looking at this, and now we're going to relate to this QC picture, is that here's our measurement node. And so your measurement instructions here are basically telling you what observable to measure. And the point is that if it's compatible, if A and B commutes, then I can first measure the quantum state here, right? And then I can feed it to this classical post-process sometime later. So in other words, we don't need quantum memory. If these are compatible observables to do this measurement node, we don't need to store rho until we get the measurement instructions. We can measure it right away. And then what we store is classical information. We store the outcome K, then we get our instructions X, and then we do this post-processing and we get out C. So this is kind of the main take-home, like the main take-home idea here is if you have compatible measurements that you're trying to do at some node, then in fact, you don't need the quantum memory, you just need classical memory. Right, okay. All right, yes, the classical instructions X can be delivered asynchronously with the quantum system, which is good. Now, of course, yeah, so this also gets generalized for what's known as POVMs, which is like the most general type of quantum measurement. You don't necessarily need observables for that to be true. But as we know, not all sets of measurements are compatible, right? So this is one of the features of quantum mechanics is that you can have incompatible measurements. And now the situation is different. So if you have a family of measurements that are incompatible, now you need your measurement instructions to arrive before you make your measurements, right? So this is really where you need your quantum memory. You still have some classical post-processing, but the point is that this measurement device here depends on your classical inputs, X here. So the state rho, you have to store rho in some quantum memory until the classical instruction arrives. All right. Okay, so let's summarize here. So compatible memories do not need quantum memory for asynchronous control. Incompatible measurements need quantum memory for asynchronous control. All right, so this is now going back to the resource theory. We want to identify these type of measurements, these incompatible measurements, as having some sort of resource. The resource here is the quantum memory you need to perform them. It's easier to do these. So these are kind of like the free operations, and these are the non-free operations. There's some cost, there's some expense to do these, and it's the expense here is the quantum memory. All right. Okay, so let's kind of now ask these resource theory questions. And I'm just going to pause real quick. So this is going till 3 o'clock, or how much time do I have?
We were expecting to give 3:55 and plus 15 minutes of Q&A. So.
Okay.
Yeah, I mean.
So pretty much that time.
Yeah.
Okay. Let me just bring it home here, and then we can do the Q&A. Okay, so again, the goal here is to now that we've identified a resource in this measurement device, we want to try to construct a resource theory. So again, we ask these kind of resource theory questions. Suppose in the laboratory you build some classically controlled device like this, and you want to know what's its full operational power. So what can you do with this thing using the free operations? And again, the free operations are those that don't need any quantum memory to perform. So maybe this device you built, maybe this does have quantum memory. So this would be a resource, but now you want to extend it. You want to do other things with it, and you want to know what you can do without having to use any more quantum memory. Right. So this is the resource theory question. Okay. And so right. So now we go through the resource theory analysis, and let me just kind of skip to the end of what we're doing. And here's this picture here is describing like all the free stuff you can do. So N was the channel that you built in the laboratory. Now you want to convert it to another channel. And you can do some classical pre-processing, some quantum pre-processing, some classical post-processing. And here's your new channel that you've built. All right, so here's the resource theory stuff. Your free channels are compatible families of measurements, i.e. controllable devices not needing quantum memory. And your free operations are these. You can do classical post-processing, quantum pre-processing, then you have some side channel memory, classical memory, and classical post-processing. Okay, and the main theorem I want to get to here is this question of, again, when can you convert one channel to another N to M? When is this possible? And this looks somewhat similar to the statistical decision problem that we talked about in the very beginning of this talk, is that you wanted to convert one channel N to another channel M. All right, now we want to ask the same question, but we're dealing with this quantum channel. And our main result here, this is a theorem, this is a generalization of that BSS theorem, was that you can convert this measurement device to another measurement device if and only if your max payoff function is non-increasing. And now the game looks a little bit different here. So now your source here, instead of being a category die, right, we've replaced it with it's a quantum classical die. So it has a quantum output and it has a classical output. So you can think of this, your category die now has, for every letter, there's some quantum state attached to it. So X on the die would indicate some psi X. A on the dice would be another quantum state, psi A. So we're feeding that into our device where we get some outcome A, and then we have to make a decision on Z. We're trying to guess X now, right? That was the original input into our channel. And then there's some payoff function. Okay. And so our theorem was then just relating the convertibility of these devices in terms of these payoff functions. Okay. Good. So since I'm out of time, I'm going to skip the non-locality stuff, and I'm just going to jump to questions.
Thank you, Professor, for the nice talk. If anyone has questions, please unmute yourselves. I don't see any in the chat box yet. Professor, I had this minor question when we were describing channel and going over the three other components that were pre-processing, post-processing, and there was a side memory. Why is it called side memory?
Because that memory is actually not going. That channel is not going through the main channel. Let me go back. So okay, here's one example. So it's side memory. So you're not going through N. N is the original channel. Or maybe this was the picture you're referring to. This, right? Side memory? Yeah, okay. So the idea is that you can think about this. I've drawn this in terms of like changing locations in space. So I imagine I have some initial point here, Alice's laboratory, and here's Bob's laboratory. But I could also think about this in time as well, right? I could think about this maybe happening, my input is today and my output is tomorrow. And then what I'm saying is that I might need to store some side information in a memory that's going to hold it in place until tomorrow. And I want this memory to be noiseless. So I'm not going to send it through any channel, but it's just going to be some side information that's preserved over time. And so that's why I call it side memory.
Okay, thank you.
I've got a question as well.
Yeah.
This is maybe more of a silly question, but it's not really, it's just sort of about terminology. And so sure. I noted when you were introduced the term supermaps and quantum combs. And yeah, as we probably discussed before, my group, for example, does a lot of work on what we call quantum frequency combs or biphoton combs. I'm imagining there's absolutely no relationship between the use of those terms, but there might be. And so that's what I want to ask, if you had any insight into where that term came from, at least, and if it at all relates to the term we use it, that would be kind of cool to be aware of.
Okay, so the answer I'm going to give is not deep because I don't think there is a deep answer. But if you look at this object here, these are like, it's supposed to be like teeth of a comb.
Hmm.
And so that's really what it is, because the idea is you could imagine you have many channels lined up, and then you have a lot of these pre-processing posts, and then you have side memory, and it'll start stacking up to looking like a comb.
Okay.
And so maybe it's just by the way that it looks, but I don't think there's anything deeper than that.
Okay. All right. That's fine. Actually, if I think back and when people started using the term frequency comb for classical laser frequency combs back around 2000, there were indeed pictures of, people would make slides where they had a picture of a, physical comb.
Yeah.
A picture of a bunch of lines poking up with the different frequencies. And
yep.
That was also based on sort of the way it looks. So
the appearance, yeah.
In some sense, there is a relationship, I guess. Okay, thanks, Harry. Thank you.
No problem. No problem.
I was curious. So I'm really familiar with a lot of, especially the earlier part of your presentation, as it relates to trying to find ways of quantifying entanglement and what it means for some states to be more entangled than other states.
Right.
And then your latter part, it makes sense. If you have a really robust theory, you can figure out how to use the resources you have to most efficiently accomplish any quantum algorithm. I was just curious, I didn't quite get to read through all of it in the middle of the presentation. You had that table with several different resource theories. So in my mind, I can think of two main categories of resource theory, that for quantifying entanglement and that for accomplishing operations. What are the other resource theories for?
Okay. I can just describe some of these. So another one, okay, so one is the thermodynamics one. In fact, this is maybe the earliest one. So this is a thermality. So here your free states are your thermal states, or rather your Gibbs states. So you imagine that you have reached your system has reached some equilibrium with a bath. And then your thermal operations are energy preserving. So you're allowed to now do some sort of unitary that's preserving energy. So it commutes with the Hamiltonian. So this is what's known as the resource theory of athermality. And then you ask the same questions here. What are the type of transformations that you can achieve using these thermal operations? Another one is asymmetry. So here actually your resources is asymmetry. So it's kind of the free states are states that have some sort of symmetry to them, and the idea is breaking symmetry is difficult to do. And so where does this kind of come into play? This comes into in shared reference frames. So if you're trying to share, if you're trying to coordinate two different reference frames between two laboratories, here you would ultimately need to break some sort of symmetry. If I need to indicate to you a certain direction in space, I need to break some symmetry. Otherwise, if everything is symmetric, then there really is no direction, no up or down, because I can just rotate it and everything looks the same. So if I need to coordinate to you a certain direction in space, I have to break some symmetry. And that's kind of where this resource theory of asymmetry comes in, is in this perspective of shared reference frames.
Okay, so would that relate to quantum states in that way, or that just relates more to how a measurement apparatus is designed? That
would be more state-based, I would say. Okay. The asymmetry is,
All right, thank you.
Yeah, and then so then there's others as well. I mean, I'd be happy to chat more at any time on these. There's a long list.
Thank you.
Yeah.
Okay, if there are no other questions, then I would like to thank Professor Chitambar for accepting our invitation and for the interesting talk today. And I would like to encourage the Purdue audience to use the Uber Eats voucher. Thank you, everyone. And with that, we would like to conclude this event.